Hello everyone, I'd like to present my recent work on testing for node change in time-dependent ensemble of integral curves. My name is Lyudmila Sakhanenko, I'm from Michigan State University, and this work is joined with my former PhD student Junet Gu. She's now a postdoc at Fred Hutchinson's Cancer Research Center. The setup is as follows. We have a vector u in four-dimensional compact space. X corresponds to a location in space and t corresponds to time. Du will denote a vectorized representation of a symmetric positive definite tensor field. V will denote the unit vector, eigenvector associated with the tensor corresponding to the largest eigenvalue. XST would be the unique solution of the following differential equation, where you can see this is an integral curve where t serves as a parameter, and this is an ensemble of integral curves driven by the vector field v, and we will be given a fixed tensor matrix B. We will have UI that are IID uniformly distributed random variables in the compact set in R4. Xi would be IID zero mean unit variance random vectors independent of the locations UI. And we observe this system of regression equations. YUI is B D UI plus sigma 1/2 UI Xi. Sigma u would be a n by n symmetric positive definite tensor that is assumed to be locally continuous with respect to special points x at fixed time t. And the main goal is to test null hypothesis that there is no time change in the ensemble of integral curve, or there is. This problem is motivated by longitudinal diffusion tensor imaging study. And DTI stands for diffusion tensor imaging, which is a popular brain imaging technique. It's widely used because it's non-invasive, it's in vivo, it only uses magnetic fields, no radiation of any type. So it's a special kind of MRI. However, it is famous for having a notoriously high level of noise that comes from biological motions, measurement errors in the scanner, and the movement of the subjects. Basically, given a set of images of the same brain scanned under the same conditions, but at different times, at different visits to the clinic, we'd like to test if there is any change in the fiber structure over time. The scientific background of diffusion tensor imaging is that there is a lot of water in living biological tissues, and those water protons, they behave as gyroscope in the presence of magnetic field. So if there is no constraints, the molecules in the presence of magnetic field will line up and tilt and spin the same way. However, if there is something in the way, you're gonna bump into it and wobble, and that could be observed, and it's measured by diffusion tensor D. In cerebral white matter, diffusion is typically anisotropic, and in the cerebral gray matter, it's isotropic, it's basically free water. The principal eigenvector would show dominant directions of the diffusion, and they usually line up along the axon. So if we follow that vector field in small steps, we can reconstruct the axon, we can reconstruct the fiber structure in the brain. However, the diffusion tensor is not measured directly. It's a slope in a system of regression equations with noise. Here's a typical image for a fixed time frame. This is a gray image of the brain. And right here, this is the estimated fiber starting at this location, and the blue tiny ellipsoids around it, these are confidence ellipsoids. Now, the goals of this study would be to look at the ensemble of neural fibers together and estimate them and provide uncertainty quantification using confidence regions, and then test whether there is a time change or not. The approach has several steps. So the first step is ordinary squares estimator of the diffusion tensor at fixed location ui. Then they are smoothed using kernel smoothing of this kind to obtain the value of the estimated diffusion tensor at any location u. Kernel and bandwidth would have to satisfy certain conditions. Then we take V to be the principal eigenvector, and then it's used to construct an integral curve estimator right here. So we follow this eigenvector in small steps along the curve. The main results, we have several. First one, we have uniform consistency right here under certain conditions on the bandwidth, of course, and under suitable conditions on the kernel and vector field and tensor field and everything. If we ask the bandwidth to behave like this, then the sequence of stochastic processes converge to a sequence, converge to Gaussian processes. Right here in the space of R3, valued continuous function on 0, capital S, where time t is fixed and it serves the role of a parameter. We have certain mean and covariance functions. They are very complicated expressions that are solutions of certain differential equations. Finally, we can construct a test statistic of this form, where notice this weight W would be chosen by a user, or it could be related to this guy. And then we construct a vector out of those values. And this vector asymptotically on the null hypothesis has a centered normal distribution with a certain covariance matrix C0, whose components are related to the limiting covariance of the Gaussian process. So then we're going to reject null hypothesis of no time change when this quantity exceeds a chi-square critical value. We've done extensive simulations with artificial data, and this is just a snapshot of one of such studies. We were analyzing the level behavior and power behavior of the procedure, which was very nice. And then we also have a real application, and that would be this example. So we have a healthy male brain was scanned 19 times throughout this time period from July 2014 to December 2018 under the same condition on the same scanner. And these are the parameters of the scanning procedure. They're here. And we analyzed this data set. We failed to reject null hypothesis. And this shows a one slice and for the last time frame. And this right here corresponds to the confidence ellipsoid surrounding the fiber, but then the fiber also moves in time. So therefore you have this graphical representation. And that was the real example that motivated the whole study. In conclusion, we constructed a test that assesses the time-dependent ensemble of fiber trajectories using the whole brain information. It has good level and power performance, even when the number of time points much smaller than number of spatial points, which is realistic in usually that's what happens in diffusion tensor imaging studies. And the last step, we're going to extend the study to tensors of high order, which is what's now more popular in imaging procedures. Finally, I'd like to acknowledge the support of NSF. We're also grateful to Professor David Zhu, who gave us the data set, and the paper has been submitted to Statistical Science. Thank you.